would be a continuation to the video in which we were practicing matrix operations, and let's continue with problem number 9. So problem number 9 and 10 in NCERT are quite similar. So I'll do problem number 10, and 9 will be quite similar to that, so you can take it as an exercise. So taking problem number 10, you have two matrices, and you get those two matrices, you add two matrices, and those two matrices are formed by scalar multiplication. So in the case of the first operation right here, 2 multiplies with all the entries, so 2x, 2z, 2z, 2y, 2y, and 2t. In case of the second matrix right here, you again do the scalar multiplication. So 3 times 1 gives you 3, 3 times -1 gives you -3, 3 times 0 gives you 0, and 3 times 2 gives you 6. And then you add them, even before doing that, let's solve let's reduce the right hand side. So in this case, you are multiplying 3 with all the elements right here. So 3 times 3 is 9, 3 times 5 is 15, 3 times 4 is 12, and 3 times 6 is 18. Now you add the two matrices on the left hand side, and you have to get the matrix on the right hand side. So 2x plus 3, 2z minus 3, 2z minus 3, 2y plus 0, so just 2y, and then 2t plus 6, 2t plus 6, and this is equal to the matrix on the right hand side, which is 9, 15, 12, and 18. Now you have four equations which can be found from this. So let's solve them right away. So 2x plus 3 equals 9, 2z minus 3 equals 15, 2y equals 12, and 2t plus 6 equals 18. Now you can solve these equations. You would get x equals 2, z equals 9, y to be equal to 6, and t to be equal to 2. And t to be equal to 6, sorry. And once you get this, you essentially have solved the problem number 10. Let's continue talking about these problems, and let's do one more problem. So you are having 2 column vectors, and adding them gives you third column vector. So x multiplying with all the elements right here, so 2x, 3x, plus negative y, so y times -1 is -y, and well, y times 1 is just y, and that is equal to the column matrix 10, 5. And now you have to add these two column matrices, so you get 2x minus y and 3x plus y, and this is equal to the column matrix 10, 5. So you are now left with two equations. 2x minus y equals 10, and 3x plus y equals 5. 3x plus y equals 5. You add these two equations, since this is just a linear equation in two variables. You add these and you get 5x equals 15, so x equals 3. Use x equals 3 and put it into this first equation. So 2 times 3 minus y equals 10, or you can write this as 6 minus y equals 10, or y is equal to -4. Okay, so you have solved for x and y. Let's continue. Now, problem number 12 is quite similar to the ones that we have been discussing till now. So you can take it as an exercise, maybe take a screenshot or something, and let's just get moving forward. And here we have a really interesting problem. So it says that this matrix, this notation f of x represents a matrix that is full of functions. This matrix is made up of functions, and we have to show that if you multiply fx and fy, that results in the matrix f of x plus y. So let's firstly write f of x. f fx. So fx, you just write the matrix already that you have. So cos x minus sin x, 0, sin x, cos x, 0, 0, 0, and 1. And then you have to write fy. So here you are just going to replace x with y. So now you write cos y minus sin y, 0 again, sin y, cos y, 0, 0, 0, 1. And then what you do is you multiply. You multiply these two matrices again by taking the dot product. So I guess I erased that, sorry. Now, once you do that, you arrive at multiplying this by this. Then, if you do the operations, you would get cos x, cos y minus. Let me expand the matrix a bit. So the first entry would be cos x, cos y minus sin x, sin y. The second entry would be minus cos x sin y minus cos y sin x. And you could continue writing this, and let me just enumerate whatever it will be. You would have sin x cos y plus sin y cos x, then multiplying these two things, these two rows and columns, you would arrive at cos x cos y minus sin x sin y, and for all other entries, you have 0, 0, 0, and for the last entry right here, you have to multiply this row with this column, so you just get 1 right there. Great. Now here comes the part where you need to apply the knowledge that you would have gained from trigonometry, and that is that cos of x plus y, cos of the sum of two angles, is equal to cos x cos y minus sin x sin y. And if you carefully observe, there are two instances where the same form happens: cos x cos y minus sin x sin y. So instead of these two places, you can just write cos of x plus y. You can write cos of x plus y. Let me write that. Cos of x plus y. Again, cos of x plus y. And proceeding similarly, if you want to write out sine of the sum of these two angles, x and y, that would be equal to sine x cos y plus cos x sine y. And if you look carefully, this is the same thing as this. So this is equal. This is in fact is equal. It's equivalent to write sine of x plus y here. Sine of x plus y. And also if you put a negative sign here, so negative of sine x cos y, and then subtract, and again a negative cos x sine y, you also put a negative here. So I did this in order to get it in the form of the entry A22 that we A12, first row and second column. And so this thing right here, this entire stuff right here, is just equal to minus of sine x plus y. Okay, so we have simplified the product of fx and fy into a matrix like this. Let's write down the right hand side. So in the right hand side, instead of writing x's here, you are just going to write x plus y. So cos of x becomes cos of x plus y, minus sine x becomes minus sine of x plus y, 0 just remains 0, sine of x becomes sine of x plus y, cos of x becomes cos of x plus y, 0 again remains 0, 0, 0, 1. And now these two matrices are equal. So you have shown that the product of the two matrices denoted by fx and fy is equal to the matrix denoted by fx plus y. Great. So this problem, if it was difficult for you, it just involves doing some extra algebraic manipulations along with some trigonometric sum formulas. So you can note it down, or you can keep it in mind that sometimes in matrix algebra you also need to apply your knowledge from other fields of mathematics, in this case like trigonometry, to reduce it to a simpler problem. So let's move on forward. So this problem right here essentially tells you to show the non-commutativeness of matrix multiplication, in matrices. And you can easily do that. What you just have to do is you have to multiply these two matrices first on the left hand side, and then multiply the matrices on the right hand side, and you won't get an answer that would be equal. And so that's a thing that we have discussed in a video when we were talking about matrix multiplication. So I'll just leave that as an exercise, and it will give you some practice of matrix multiplication, so that you can try this problem yourself. Let's move on forward. Now we have two problems that are quite similar. You have to find the value of an expression. So instead of having something like x squared minus 5x plus 6, wherein you would have put some value of x, instead you're having a matrix equation wherein you put a matrix to get the answer. So you would have computed a squared. A squared is just a times a. You'd have then multiplied it with 5. Then you would have tried out finding, sorry, not this. Then you would have tried out finding 5 times a, negative 5 times a, whatever that answer would be. And then you would add 6i to it. So in this case, I would be the 3 cross 3 matrix. And once you get all of them, you add them to get the final answer. But I'll attempt problem number 16, and problem number 15 is a bit easier than that. So what do we know about this problem? So we know that we already have a, we already have the value of a, we already know what I is. It's a 3 cross 3 matrix, 1, 1, 1 in the diagonal, and zeros at all of the rest places. So now you have to compute a squared and a cubed. So let's do that. So writing a, you get 102, 021, 203. And if you multiply a with a, you are getting a squared. So again, let me write a 021 and 203. Now if you multiply it, so you have 102 here and 102 here. So it becomes 5. You can try multiplying it, and it will result in the number 5. Then you have 102 being multiplied by 020, and you would have the answer 0 in this case when you do the dot product. Then you have 102, and you're multiplying 102 with 213. So 1 times 2 is 2, 0 times 1 is 0. So 2 plus 0, and then 2 times 3 is 6. So you get 508. And you can continue doing that. So let me just compute that for you so that we can proceed with the problem. So you would have 2 here, and you would have 4 here. Then you will have 2 plus 3, 5 here. You would have 2 plus 6, 8 here, and then you would have 0 here, and then at last you would have 4 plus 9, 13 here. And this is equal to a squared. So now the value of a squared that you have computed is 508,245,8013. Okay. And then you figure out what a cubed will be. So a cubed is just a squared times a. And you can do that. You can figure out what that will be. And once you find out the value for a cubed, you'll put everything back into this equation and solve this equation. And hopefully you will get once you compute this entire left hand side, you would get that to be equal to the zero matrix of the order 3 by 3. So that would be some sort of a numerical exercise. If you want to skip it, you can, because we have plenty more problems that we can consider solving. So here we have problem number 17. That's a bit less on the computation side and a bit more, I guess, on the mathematical side. So you have two matrices, a 2 by 2 matrix, and I, that we know, the identity 2 by 2 matrix. So you have to find a number k such that a squared equals ka minus 2i. So let's first figure out, you know what a is, you know what I is, you know what 2 is, obviously, and you want to find what k is. So let's first compute what a squared is. So a squared is just a times a. So 3 minus 2, 4 minus 2, 4 minus 2. And again, you write the same matrix. So 3 minus 2, 4 minus 2. And you multiply these two matrices, again using the same technique of dot products. So in this case you would get 9 minus 8, that will be 1. Then you would have minus 6 plus 4, so minus 2. And then you would have 12 minus 8, so that will be 12 minus 8 will be 4. Okay, so you would write 4, and then for the last entry you would have minus 8 plus 4, so that will be minus negative of 4. So that's the value of the matrix A squared. So A squared has to be equal to some, let me erase the extra A's here. So A squared has to be equal to some constant k times the matrix A, which is 3, negative 2, 4, negative 2, minus 2 times the matrix I, which is 1, 0, 0, 1. And now what you can do is you can do the scalar multiplication, and so you would arrive at 1 minus 1 negative 2, 4 negative 4 equals 3k minus 2k, 4k minus 2k minus 2002. And then you subtract these two matrices, so you get 3k minus 2 minus 2k minus 0, so that's just minus 2k, 4k minus 0, so 4k again, and minus 2 will get you minus 2k minus 2. And that has to be equal to 1 negative 2, 4 negative 4. And note that you have 4 equations. You can form 4 equations right here. So 1 equals 3k minus 2, negative 2 equals negative 2k, 4 equals 4k, and negative 4 equals negative 2k minus 2. And you can solve any one of them and you would arrive at k equals 1. So that was a nice problem. Let's move on to problem number 18. Now problem number 18 says that there is a matrix which sort of looks like a diagonal matrix, but it's not a diagonal matrix. You know that it has written that A is the identity matrix of order 2. Show that I plus A, the matrix I plus A, would be equal to the matrix I minus A times this entire matrix. So let's compute the unknown matrices. Let's compute I plus A. So I is 1, 0, 0, 1 plus 0 minus tan of alpha over 2, and below you have tan of alpha over 2, 0, and you add these two matrices up. So you get 1 plus 0, 1 plus 0 is 1, 0 plus negative of tan alpha over 2, so negative of tan alpha over 2. 0 plus tan alpha over 2, so tan alpha over 2, and 1 plus 0, so 1. So that's what I plus a is. Let's figure out what I minus a is. I minus a. I minus a. So you write the two same matrices, but instead now you are subtracting them. So now again you are performing element-wise subtraction. So 1 minus 0 is 1. 0 minus negative half is negative tan of alpha over 2 is tan of alpha over 2. 0 minus tan of alpha over 2 is negative of tan alpha over 2, and 1 minus 0 is 1. Okay, so you have figured out what the two unknown matrices here are. Now, on the left-hand side, you have a single matrix, which you have figured out, and on the right-hand side, you have a product of two matrices. So now what you want to do is you want to multiply this matrix by the matrix that you have, cos alpha minus sine alpha, cos alpha. And let's just do that. Let's just do that. So 1 tan alpha over 2, and then negative tan alpha over 2, 1. And you're multiplying that with cos alpha minus sine alpha, cos alpha. And if you do the multiplication, you would arrive at, I'm not walking through the steps again, you would arrive at cos alpha plus sine alpha tan alpha over 2. So it would be a giant number. You would also have here in the second entry of the first row, you would have negative sine alpha plus cos alpha tan alpha over 2. Here you would have sine alpha minus cos alpha tan alpha over 2. And the last entry of this 2 by 2 matrix that we have here would be cos alpha minus sine alpha tan alpha over 2. Okay. Now let's just move on forward with this, and here I would expect you that you know about the half angle formulas in terms of, okay, there would be a plus right there, sorry, in terms of a tan of alpha over 2. So in this instance, what you can do, so it's a bit of a long problem. So you already know what I plus a is. The left-hand side is written right here. Let me just mark that as the left-hand side. So this is the left-hand side. Now let me erase all the irrelevant stuff here. So now you have the two matrices on the right-hand side and on the left-hand side. However, you still haven't proved that these two are equal, because to do that you have to prove that all the corresponding elements are equal. So in that case, what you would do is you would see how can you equate these two matrices. So let's start with the first row, first column entries of both the matrices. So cos alpha plus sine alpha times tan alpha over 2. Now I will use the formula that sine alpha is equal to 2 tan alpha over 2 upon 1 plus tan alpha squared over 2. And this is a standard formula. And similarly in the case of cos, you have 1 minus tan squared of alpha over 2 upon 1 plus tan squared alpha over 2. And if you put that right here, you would have 1 minus tan squared alpha over 2 over 1 plus tan squared alpha over 2 plus. Now instead of sine alpha, you put this entire expression right here, and you are multiplying it by tan of alpha over 2. So you would have 2 tan alpha over 2 from the sine from the sine alpha, and you are multiplying it by tan of alpha over 2, so you would get 2 tan squared alpha over 2 upon 1 plus tan squared alpha over 2. You add these two expressions, and once you add them, it results in the following expression. The numerator and denominator are equal, so that's just equal to 1. So the first element of both the matrices are equal, and if you look at the second row, second column of both, they are still the same, and so they are also equal. These two are same, and so if this is equal to 1, this is also equal to 1. Let's solve for the first column, second row entry. So you have sine alpha minus cos alpha times tan of alpha over 2. In this case, what you do is you again put in these expressions. If you again put in these expressions, you would get 2 tan alpha over 2 over 1 plus tan squared alpha over 2 minus, instead of cos, you put in 1 minus tan squared alpha over 2 over 1 plus tan squared alpha over 2. It's a long problem, but it still does a revision of half angle formulas, so let's just do it anyways. And if you multiply these, you have 2 tan alpha over 2, and observe that 1 plus tan squared alpha over 2 is just common, so 1 plus tan squared alpha over 2 just remains right there. So 2 tan alpha over 2 minus tan alpha over 2 plus minus again, so it's just the minus sign. I have not removed the brackets yet. Minus tan cubed alpha over 2. And if you do the math, if you simplify this further, you would come at tan of alpha over 2. So you have equated this expression right here to this expression, and if you again notice that the entry in the first row, second column is just the negative of the entry you have already computed. So if this is equal to tan of alpha over 2, this entry right here is equal to negative of tan of alpha over 2, and that's the exact expression that you have on the matrix on the left hand side. So now that you have proved that all the corresponding elements are equal, you have essentially proved that the two matrices are equal, the two sides are equal, and so this equation is proven. So that was a fairly long problem. Let's do some final problems before ending this video. So 19 and 20 are sort of the practical applications of matrix, and what I will do, I will just solve problem number 20, and problem number 19 is just kind of an extension of it, so you can try it out yourselves. So the bookshop of a particular school has 10 dozen chemistry books. 10 dozen chemistry books. So let's denote chem for chemistry books. Let's do the second column for physics books, and the third column for economics books. And then you know that there are 10 dozen chemistry books, so that's a total of 120. 10 times 12. You have 8 dozen physics books, so 8 times 12, so that's 96. And similarly, 10 dozen economics books give you 120. And then the selling prices are rupees 80, 60, and 40 each. So the selling prices are 80 for the chemistry book, 60 for the physics book, and 40 for the economics book. So if you want to figure out the total amount the bookshop will receive from selling all the books, you just are multiplying these. You are just multiplying these. These are the prices per unit. So you are doing a matrix multiplication of a row vector with a column vector. And the answer would be a single number. So you are doing 120 times 80 plus 96 times 60 plus 120 times 40. And you can solve that, and whatever the answer would be is the answer right there. So in fact, we can do that. So this would be equal to 9600 plus this would be equal to I don't know, 5760, and this would be equal to 4800. And if you add them all up, you get 0, 6. I'm proceeding from the backwards, so 15 and 6, so 21, and you get a carry of 2 there. So 6 plus 5 is 11. 11 plus 9 is 20. So this calculation is completely irrelevant. The main idea is that you are using matrices, and that will be the final answer that you would get. Let's look at the final question, the final problem for this video. Assume that x, y, z, w, p are matrices of order 2 by n, 3 by k, 2 by p, n by 3, and p by k. So let's write that down. So x is 2 by n, y is 3 by k, z is 2 by p, w is n by 3, and p is p by k. So the first problem is the restriction on n, p, n, k, and p, so that py and plus wy will be defined are. So to have a well-defined matrix py plus wy, you first need to have a well-defined product py, and then you need to ensure a well-defined wy. And once you have ensured that those two matrices are well defined, you also need to check that their orders are same. They both are of the same order. If they are not, then you cannot add. So let's look at the first part. So p times y. So p is p. The matrix p is is of order p by k, and the matrix y is of the order 3 by k, and the only way that p times y will be valid is if these two numbers are equal. That's something that we discussed in matrix multiplication. So k must be equal to 3. So that's the first condition. And then you have to ensure a well-defined w times y. So y is still the same, y is still 3 cross k, and the matrix w is n cross 3, n cross 3. So now you see that both of the inner numbers are the same, so there is no restriction as such as you develop on it. Now, also one more thing. The order of py would be the order of the matrix product py would be p by k, and the order of wy, the matrix product, will be equal to the outer dimensions that you have, so n by k. So in order for, now we also have one more restriction that we have to take into account. The orders must be the same. So this must be equal to this. So k's are equal. You also must have p to be equal to n. So you have k to be equal to 3 and p to be equal to n. Let's look whether there is an option for that. Yes, there is. K equals 3 and p equals n. Let's do the final problem for this video and hopefully for this mini series. If n equals p, then the order of the matrix 7x minus 5z. So x is of the order 2 by n, and z is of the order 2 by p. So So now you're saying me, the problem is saying me that x stays of the order 2 by n, and z, since p is equal to n, you can write it as 2 times 2 cross 2 by n. So the orders of these two matrices are equal now. So any operation, we talked about that. So we talked about in the video on scalar multiplications that if you multiply all the elements by some number, so let's say you multiply in the example that in the problem that you have, you're multiplying x by 7, and z, the matrix z, by the number -5. So even if you multiply all the elements by doing the scalar multiplication, you do not change the order. So if you multiply 1, 1, 1, 1 by a number scalar 2, the matrix that's the answer to this question still has the same order as you started with. So 7x would have the order 2 cross n, and -5z would have the order 2 cross n again. So their sum 7x minus 5z would be of the same order as the contributing matrices are, which is 2 cross n. So let's look at whether we have a choice for that. Yes, we have. And I guess these two videos, the one that we have been discussing in problems right now, and the previous one, hopefully make up for a lot of practice of matrix addition, multiplication, subtraction, scalar multiplication, and I'll see you in the next videos, and we'll continue talking about matrices.